Bonjour à tous et toutes. Je me présente, je suis Valérie Lejean-Guimat, je suis la doyenne des affaires départementales. Je vous souhaite la bienvenue au nom de l'Université du Québec à Chicoutimi. La soutenance de thèse est un moment important dans le cheminement d'un étudiant-chercheur. C'est le moment de l'évaluation par les pairs, des résultats et des réflexions de votre travail de recherche en tant qu'étudiant-chercheur. Je remercie le président du jury ainsi que les membres du jury pour l'évaluation de cette thèse. Je remercie aussi le directeur de recherche, M. Bouchard, et le co-directeur, M. Valéran, en ligne, et M. Pouzois, pour l'encadrement de cette recherche et l'accompagnement de l'étudiant-chercheur. Petite anecdote. Le jour de ma thèse, le président du jury m'avait confié « Aujourd'hui, vous êtes un spécialiste de votre domaine, de votre travail de recherche. Monsieur Bagasa, je vous souhaite une bonne soutenance. » Donc, je céderai la parole au représentant du directeur de programme, qui est monsieur François Lemay, pour la suite du déroulement de cette soutenance.
Merci, madame la doyenne. Oui. Appuie sur le bouton. Ah, voilà. Donc, monsieur Bagasa. Bon, ça fait plusieurs années que je travaille sur ce projet-là, sur cette thèse-là. Il y a eu beaucoup d'efforts de fait et aujourd'hui, c'est le point culminant de plusieurs années. C'est un moment fondamental pour un chercheur, ce moment-ci. Mais dites-vous une chose, c'est que les gens qui sont ici sont des gens qui sont intéressés par ce que vous allez dire et c'est pas si facile de trouver des gens intéressés par ce qu'on fait dans ce domaine-là. Alors, je sais que c'est énervant, je sais qu'il y a un stress derrière ça, mais ce que moi je vous invite à faire, c'est de prendre du plaisir à exposer votre domaine d'expertise au public qui est ici et qui est à distance. Et je vous souhaite une bonne soutenance. Merci.
Donc, juste pour rappel, tu auras 45 minutes pour faire ta présentation. Après ça, il y aura des commentaires sur chacun des jurys, plus une période de questions. Là, en général, on fait 2 tours de questions. Okay. Peut-être qu'il y en aura un troisième s'il y a plus de questions que ça. Okay. Donc, l'introduction, ça passe quand même. Donc, monsieur Ali Bagasa, donc, vous avez présenté une thèse de doctorat qui s'appelle Pedestrian Profile Recognition Using Deep Learning on Thermal Image and Smart Cities pour obtenir justement le grade de PhD. Donc, les membres du jury ont examiné notre thèse et ont dit que c'était acceptable pour la défendre. Okay. Donc, tu peux commencer ta présentation, s'il te plaît.
Okay. Okay, so I'm going to present in English because some of the members of the jury are non-French speaking. So as you said today, I'm going to present my thesis, which is entitled Pedestrian Profile Recognition Using Deep Learning on Thermal Images in Smart Cities. I'm just starting the timer to make sure I'm not going over 45 minutes. So first of all, thank you to the jury for examining my thesis. I know it was quite long, especially literature review part, so I'm going to go to focus on the important parts. The way I'd like to present the thesis is starting by reminding the project context a bit, then talk a bit about smart homes and then smart cities. I'm going to present the prototypes I've used quite quickly, then go over the literature review, but I want to go mostly about, I want to talk about the conclusions of the literature review without going too in depth. And then I'm going to present the deep learning algorithms I've used and obviously discuss the results. So as I said, a few precisions, since there's a lot of ground to cover. Instead of just rushing through everything, I've decided to make choices about what I'm going to talk about. So I'm going to skip the very early work on activity recognition, and I'm going to skip the details about the actual prototype and the way I've built it, and the actual software implementation, as well the as the Android application development. I'm going to go quickly on the very early approaches, and my goal is to try and convey like how I got to the end point of the thesis and the lessons I've learned throughout the path or the journey of the thesis. So first, starting with the context of the thesis. So I've been doing my thesis with the LIA, which specializes in autonomous, in ambient intelligence in smart homes. So the idea is to use technology to assist semi-autonomous people in smart homes. And this is important because the population is aging. So we've got more and more people who are semi-autonomous and who need assistance. So using technology is a good way to do this. And the seed of my thesis basic question was, how do we transfer ambient intelligence from smart homes to smart cities? And that's how we started to think about it. So a quick reminder on smart homes. The smart homes are basically smart environments that are filled up with sensors. And by looking at the patterns of activation of the sensors and using methods such as machine learning and artificial intelligence-based methods, we're able to recognize the activities of people. And that means that if we can recognize these patterns, we can also see when people are behaving in an abnormal way, which means that we can give them assistance in real time. So the question is, how do we extend this to smart cities? So there's two main avenues. So you could either use environmental sensors, like we do in smart homes, or you could use wearables. So that could be smartphones, and that could be smartwatches. The good point about, say, smartwatches and inertial sensors that you're going to put on the body is that you'll be able to recognize sort of physical activities and very accurate micro activities. And using smartphones, you can recognize macro activities. So that's more depending on the location of the person in the city. You could say, well, this person is in the library, so they might be reading a book, or they're in a bank, so they might be doing any type of financial activities. But the issue with this approach, and the reason why we did not go with it, is that it's quite intrusive. Because you first need to identify people and be like, okay, so we're going to recognize your activities. So here's a smartwatch, here's a smartphone application, and we're going to learn how your activities, like the firings, sort of the patterns to recognize your activity, and then trying to use this on other people. But we wanted an approach that was anonymous and that did not require identifying people prior to the experiments, and that could work from a city perspective. So the two main modalities you could use are in the city with environmental sensors are basically image and sound. So sound is just going to be microphones, and image, you have two main avenues. So you either use RGB images or thermal/infrared images, and I'm going to talk a bit about the difference. So RGB images are going to be used standard cameras, so just putting cameras in the city. And I've decided to go with thermal images because I wanted an approach that was that would preserve people's privacy. So on a thermal image, you cannot really identify who's walking by, as you're going to see on the images, whereas RGB images can be quite intrusive. So the main difference between thermal images and infrared images is that infrared images, from my understanding, are active. Infrared cameras are active, sorry. So they project infrared light on a scene, and based on the light that comes back to the sensor, they build an image, they construct the image. Whereas thermal cameras are passive, which means that they're actually thermal sensors, and they sense the heat in the scene, and from the heat, they reconstruct the image, which means that you have less details and texture, the contours can be blurrier, and there is a higher impact based on the clothing that the person is wearing. So it's generally more challenging than using infrared images. So going over the first prototype, the idea behind the first prototype was to build sort of the cheapest prototype we could build that would consume the least energy and see what is doable with this prototype. So I used an Arduino Due board and a basic 8x8 infrared array and a basic microphone that was picking up sound at 100 hertz frequency. At this point, I was still in the mindset of extending the smart home approach to smart cities. So I was still interested in activity recognition at this point. So I did mainly 4 tests with the data collected. So the first one was recognize the presence or the absence of pedestrian in front of the sensors. Then it was age, activity recognition, and group size recognition. So for age, it's basically 3 categories: so child, adult, and elder. And there were some basic activities, as you can see on the slide. The first results, basically, there was just one experiment, 140 pedestrians during this experiment. And we've basically used conventional machine learning approaches, so random forest, support vector machine, multi-layer perception. The way the features were collected is basically after synchronizing the labels that I've collected on the Android application and the actual data of people passing by in front of the sensors, I've created a fixed size window. And from this fixed size window, I've extracted different features coming from the microphone, as well as the grid eye sensor. In terms of results, I don't want to go too deep in the analysis of these results, first of all, because we're only talking about a very small sample size. So that's just 140 pedestrians. So there is a chance that some of the results could have a lot of noise in them, and it could be due to chance as well. But first of all, 94% accuracy for presence or absence basically means that the sensors worked. So that's a good point. And then for age and activity recognition, what I realized when I analyzed the results is that because of the location of the nodes, basically I put 4 nodes in the city about chest height. Because of the location of the nodes, the activity and the age could be inferred quite quickly, just based on the height of the silhouette. So that was one of the factors that sort of optimistically affected the results. And so the experimental setup was quite limited, and the sensors we're using were quite low resolution. So basically that's an illustration of the 8x8 array that we're building. So like in theory, it should capture a silhouette, but in practice, it's quite hard. And at this point, I realized I'm asking the wrong question, actually. I'm trying to recognize people's activity in the city, whereas in smart homes, you have a strong correlation between the location and the activity that's being performed. So you're going to brush your teeth in the bathroom, you're going to cook in the kitchen. And in the city, the concept of activity is much fuzzier because you could be performing any activity anywhere. And when you're deploying an experimental setup on a portion of a pavement, you're basically going to be capturing all sorts of activities, but they're mainly going to be walking related activities. So then I realized that, well, the overall goal is to extend ambient assisted living from smart homes to smart cities. So first we need to recognize who might need this ambient assistance, which is when the thesis sort of steered towards profile recognition at this point. And that's when that leads us to the second prototype. So the second prototype was built using a Raspberry Pi that we had in the lab. The goal at this point was we want better results. We want higher resolution sensors. So that's when I used a thermal image, an actual thermal image, rather than just an 8x8 array. And that was the FLIR lepton that captures images, as you can see on the slide, at a resolution of 160 by 120 pixels. And each node was also equipped with a microphone. And basically, I wanted to try 2 cameras. So there was a smaller camera, 32 by 24. But I did not end up using this camera because I had to basically choose which modality I wanted to use. My idea was just to collect as much data as possible during the experiment, then go back to the lab and see which one I want to work with. But then in the future, there's avenues for using both images and sound and perform sort of multimodal profile recognition, gait recognition. In terms of the experiment, so you can actually see on the image, that's the actual location of the 2020 experiments. So I was sitting on the bench there in front of the town hall, and basically the nodes were just set at the base of the trees. And I was just sitting and using the Android application, and I was trying to simply collect the label of the people passing by at the moment they stepped in front of each node. At the end of the day, I only ended up using the data from the central node, which was equipped with the best camera, and I discarded the other nodes. But there was also an idea of trying to perform distributed profile recognition, but we've left that to the side. There were many avenues in the thesis that we've left to the side because we had to focus on something. So in terms of the 4 main tasks that I'm trying to do, it's age recognition, gender recognition, mobility recognition, and group size recognition. So that was just binary each time. So total of 10 experiments. And we've also asked for the an ethics certificate to be like all legal to do the experiments. Turns out that because of the specific modalities of the experiment, we did not need we're exempt from an ethics certificate because we're using anonymous sensors that don't allow the identification of people in the street. We're doing this in the public space and we're not interacting with the people during the experiment. So basically I'm just sitting on a bench and I'm just watching people going by, but I'm not interacting with them, so not asking them any information. So that's an example of the data that we collected. First one is sort of the textbook perfect case where you have just one adult male walking by in front of the frame. There's no one in the background, there's no car in the background. That's just perfect for gait recognition perspective. The second one was I wanted to show a few different cases. So first, the image on the right, you can see the overlap between a silhouette and a car, and that's going to happen a lot in the data because both objects emit heat. So you're going to have an overlap, which is going to make the task a bit more difficult for the models to tell the silhouette apart from the background. And also the groups, there was like something quite interesting is that usually people start out being spread out. And because of the angle of the camera, when they walk by in front of the camera, they just sort of merge before spreading out again. So that could also be confusing for the algorithms when doing group size estimation. In terms of the third one was, what I wanted to illustrate on the third one was, I don't know if you can see clearly the difference in silhouette size, and also the fact that a lot of the silhouettes actually were cropped at shoulder level or head level. So that's going to be another challenge. If you're not dealing with the entire silhouette, you have less information, especially the head that could help recognize a gender, for example, even if it's less clear on thermal images. On the fourth one, there were some different cases. For example, someone on a wheelchair, what I call the scooter in the application, which is actually an electrical wheelchair. Someone on a bike, someone riding a skateboard, and someone walking a dog. So these were my sort of activities. When I'm talking about activities, someone riding a bike, riding a skateboard. So the lessons learned from these experiments are first, nodes should be invisible. If we're trying to embed, to have ambient assistance in the cities, the prototypes or the nodes we use should be invisible because, first of all, when people feel observed, they're going to walk in a different way. And I've also had, in one instance, a pedestrian that I was doing the experiment and the pedestrian just picked up the node and started walking away with it. So I had to stop the experiment, run after the guy and ask for my node back. So that shows that we need the nodes to be invisible. The importance of node positioning as well, because as I said, you want to capture as much of the silhouette as possible. But the thing is that in real life, if we have no control over the way people walk in the city, which means that no matter where you put your node, you're going to have partial silhouettes. So I think even though we don't have full silhouettes, we're actually working with a very realistic data set for what would be a live implementation. Some choices have to be made during the experiment. When you have two people of different profiles that walk by around the same time in front of the camera, as an observer, I had to make choices. So I had to decide which profile I was going to record because I cannot move my fingers fast enough to record two very different profiles at the same time. And I ended up trying to boost the minority class, which was the elders. And that was also the population I was interested in. In terms of the synchronization, the way I synchronize, because if you're recording labels on an Android application, and if you're recording data on a Raspberry Pi using a thermal camera, you're going to have to synchronize the labels, the timestamp of the labels with the actual observation. So I did that using an anchor observation. So basically, I'm capturing an observation that I know of at the beginning of the experiment. And then I'm using this to synchronize all subsequent observations. But ideally, in future experiments, you want to have a real-time synchronization, or at least timestamp synchronization between the tablet and the nodes. That would make it much more practical and accurate. Some of the challenges and obstacles, we're dealing with thermal images. So as I said, there's less texture, less details. We're working with low resolution images as well. And I've made the conscious choice of not processing the images, which could be questionable, but I'm going to get to this later. Basically, you could extract the silhouettes and then just work with the silhouettes. So that you'd be sure that most of the image is information, useful information. But my idea was to have sort of a black box approach and to see how far we could push deep learning and be like, okay, we're just using deep learning and we're seeing how far we can go in terms of profile recognition before addressing the sort of pre-processing part. And also at this time, I thought that if I had a method that could extract the silhouettes on images in the lab, I thought that I had no way of knowing if I would be able to do it on unseen data in real time. But actually, there are ways to do that. There's also fuzzy interclass boundaries. So what is an elder? I'm defining someone as an elder if I assume that they're over 65 years old, because that's what's used in the literature. But I have no way of knowing if they're really over 65 years old. And also we're dealing with a small data set, which is going to be an issue along the thesis. The first CNN approach was, the goal was to have the most straightforward implementation possible, which means that at this point, I'm not really sorting data. So that means I'm performing age and gender recognition on people on a bicycle, on people in a wheelchair, and I even left groups at this stage. Because the idea was to see, well, what can a CNN do on this? So we're using a 2-layer shallow CNN on the data to try and perform profile recognition. And in terms of results, first I'm using 5-fold cross-validation, important to specify. So 80% of the data is used to train the models, and the 20% left are used to have validation results, which are the results I'm presenting. First of all, in terms of the results, what we can see is that mobility seems to be the easiest task, mobility recognition, followed by group size, gender, and age recognition. It makes sense because the thermal signature of someone on a wheelchair is going to be quite distinctive from someone who's walking and mobile. Whereas if you're trying to estimate, to recognize the age or gender of someone, it's going to be much harder on thermal images. In terms of group size as well, you have the sort of silhouettes merging that you can generally tell that there's more than one person on the image. The conclusion about this is that I realized that I have made one important mistake at this point, which is that I always had different images in the training and validation data set, but sometimes I had the same person in the training and validation data set, which means that the CNN actually could sort of recognize the silhouette of the person and find their profile by association. So that's not direct profile recognition. And there were some hidden correlations in the data set as well. So someone who is in a wheelchair is going to be an elder 99% of the time, which means that trying to recognize their age, well, there's going to be some hidden correlations there. Also, we're not processing the images. So sort of 70 to 80% of the images is just noise. That's not useful to the CNN. So that's what's limiting the results, what's negatively affecting the results. Just zooming back at this point. So that's basically a snapshot of the thesis in one image. So the first 3 columns are the actual thesis I've presented. The 4th column is what I've been working on since then, which has taught me a bit more about the problem. And that's where we are right now. We just presented the results of the second approach, second column. And at this point, well, before switching, at this point, I realized that we can solve the problem. We're getting results that are better than average or random guesses. But the CNN, the shallow CNN approach is quite limiting. And at this point, I realized, well, I need more knowledge in deep learning and I need more knowledge in gait recognition. So that's when the literature review part starts. I'm going to go quite quickly on this. But basically, what is gait recognition? Gait recognition is recognizing one person among a set of different people. So not exactly what we're doing right now. There's a trend towards deep learning. So in recent years, people have realized that, well, in challenging conditions, you actually want to use deep learning to deal with background noise and sort of challenging environments, because most of the available gait recognition data sets are actually captured against static backgrounds. So the silhouettes are easy to extract, but it's not really realistic in terms of application in the city. I've realized also that in the gait recognition literature, people tend to use the entire sequence of the image, which is why I use RNNs later in the thesis. So basically, you extract features of the entire sequence of gait energy image, and you use that, you feed this to a deep learning model. One of the main challenge of gait recognition is dealing with gait covariates. So depending on the angle the person is captured walking at, and depending on the clothing and accessories they're wearing, you're going to have accuracies that are going to be quite different. So it's going to be different to recognize the same person at a different angle, for example. Now that leads us to profile recognition. So there is much less research in profile recognition compared to gait recognition, which is also called soft biometrics recognition, technically. There's a similar deep learning trend at this point. And one of the main takeaways from this is that knowing someone's gender makes it easier to guess their age. So if we were to recognize people's profile in the city, it would be smarter to start by recognizing their gender and then recognize their age if you want better results. And at this point, gait covariate are still a big challenge. So the first infrared based approaches, because we're working with infrared with thermal images, but the first infrared approach was done in 2006, and then there was not much work on this until it recently picked back up. And to my knowledge, the best approaches have been using a fusion of RGB images and thermal images. And the best results using thermal images only are slightly above 83% for gender recognition. So that leads us to the deep CNN optimization. So at this point, I'm like, okay, I'm going to do things properly. And I'm going to optimize a deeper CNN. So first of all, I'm dealing better with my data. I'm shuffling it better. I'm excluding, if I'm doing age and gender recognition at this point, I'm excluding wheelchairs and I'm excluding people on bikes, because there's not much sense recognizing, and groups as well, there's not much sense recognizing people's age on a bike. It's maybe not what you're interested in. And in a group as well, because it doesn't really make sense to recognize the gender of an entire group. And at this point, I'm still using the same strategy, but I'm going one step deeper. So I'm using 80% of the data to train the model, 20% to validate it, and then another bit of data that's going to be the results I'm presenting, on which I'm running the train algorithm. Because the idea behind this is that I wanted a completely independent data set to make sure that none of the people of this data set had been seen by the model before. So the results are more robust this way. At this point, I'm just adding layers until the results do not improve anymore, or until my GPU cannot take it anymore. In terms of the data, that's we're ending up with the CNN, we're ending up with around 3,000 images total. And the main point in the data, well, two important things. First, there's a high variability in the data. So depending on the angle of people, because we have no control over the way people walk, depending on the angle they walk at and the background noise and the temperature of the day, we've got a very high variability, which makes it really challenging. And I've actually counted the silhouettes that were cut, as I said, at the head or shoulder or below. And it turns out that about 55% of the silhouettes are partial. So we're working with more partial silhouettes than entire silhouettes. In terms of the architecture, well, the details of optimization are in the thesis. I don't want to get too deep into this, but basically it's a mix of grid search and random search. So I'm just varying one parameter, seeing the results and varying it and doing it again. And sometimes I'm just casting like a random guess to see if a widely different architecture is going to give better results. And I'm using image augmentation as well. So that's applying random transformation on the images so that the CNN can generalize better. So the final architecture has 15 layers for the CNN and a dense layer containing 512 units. And that seemed to be on par with what's done in the literature. So in gender recognition, they realized that starting from 4,000 units on the dense layer and going down and down, they realized they had better results with smaller dense layers. But I just found this experimentally, and then I realized in the literature that was congruent. In terms of the results, so it seemed like above 8 million parameters did not give better results. Actually, the models started overfitting. The best architecture, I already talked about this. And here we see a similar trend with mobility being easier than gender recognition being easier than age recognition, but we're actually getting worse results than with the shallow approach, which shows the impact of the hidden correlations and the sort of people that were recognized in the training data set and the profile being inferred from this. But these are actually much more realistic results, and they're a much more realistic baseline to start from. And after this point, I wanted to see, because the idea is to recognize profiles in real time in the city. So I wanted to see, can we embed these algorithms and have them run in real time on the Raspberry Pi. So I've trained compact models. So I just stripped away the biggest layers, the deeper layers of the CNN, and retrained the algorithm, took these algorithms and ran them on Raspberry Pi to perform classification. First of all, important point is that smaller models actually perform better for mobility recognition. So which shows that it's quite an easy task, and a smaller model would be enough to perform almost 99% accuracy for mobility recognition. But the models we had a drop of from 10 to 15% in accuracy for age and gender recognition on the Raspberry Pi. I could not pinpoint, or at least I did not take the time to pinpoint the exact issue on the Raspberry Pi, but I think it might be coming from a floating point imprecision that would be carried out through the layers of the models. And you start with slightly different neural activation that get more and more different. And at the end of the day, you get misclassifications. But at this point, I realized that simply based on the time of classification, simply the Raspberry Pi is not the right board to use for deep learning. We're using TensorFlow CPU as well, that could have an impact. So I realized that in the literature, they do not use Raspberry Pi for deep learning. They use boards such as Jetson TX2, sorry. So if I'm doing this, if I'm implementing the algorithm in real time, I'm going to use one of these boards and then see and solve the problem if there is any. So in terms of the conclusion about the CNN, so we're working with a challenging data set. We're not pre-processing the images, so there's a lot of noise, and there's a lot of partial silhouettes as well. At this point, we can decide to manually extract the silhouettes, use another vision model, use both image and sound, but that would require a lot of pre-processing on the sound as well, or use a sequence of image, which is the avenue I've picked because of what was done in the gait literature. So at this point, I was going at it from a gait recognition perspective, which is why I use a sequence of image and not a silhouette extraction. And at this point, I have a choice, main choice is choosing between the GRU and the LSTM. At this point, I decided to choose the GRU because the LSTM was longer to train and it seemed more appropriate for longer sequences. And I did not necessarily need that because I'm working with sequences of 2 to 6 images. And the way this works is that the CNN is going to extract the features of each image in the sequence. And every single one of this set of extracted features is going to serve as an input on the RNN. And then the RNN is going to learn temporal relationships between the extracted features of each image in the sequence. And I've also used a try with bidirectional GRU to see if we get better results by learning temporal relationships going in both directions, past and future. Quick point on the data set here. Data set is even smaller because we're using sequences of images. So what used to be one observation equals one image. So one sequence equals one observation. So we're working with slightly over from 130 to 150 instances only, which is not much for deep learning, to perform age and gender recognition. And at this point, I'm dropping mobility recognition because there's so few instances and we're already getting very good results just using a CNN. So the architecture, same strategy, mix of grid search and random search, using 2, 4, or 6 images per sequence. And I'm just using the same CNN architecture. But the main point was to find the right recurrent layer size, a number of epochs, and the regularization in the model. In terms of results, for the first time, we can see the trend has shifted. So actually, you're seeing that age recognition is 79.5% and gender recognition is under 79%. Once again, these are quite close and we're dealing with small data sets, so it's not exactly sure if it's statistically significant, but it seems that using a sequence of images could lead to better results for age recognition. But at this point, it's just a hypothesis that needs to be checked. But what's more important is that we're getting a 14% increase in age recognition accuracy and 8%, slightly more than 8% increase in gender recognition accuracy using a sequence of image compared to using a single image. At this point, I think what's happening, maybe I'm talking about this here, yeah. What's happening is that by learning the temporal relationships in the sequence, at least what I think is happening, is that the model is actually learning where the silhouette is because it's learning what's changing in the sequence, which leads it to look at the silhouette more than the background, which possibly extracts more gate-related information, which improves the results. But the issue with that is that even though there is better potential than using a single image, it's that when you have several objects on the image or a car going in the background, you're losing a bit of this effect. So at this point, I realized that I had to move towards object recognition. So I had to extract the silhouette and be sure to only work with the silhouette to do profile recognition. So I'm going to conclude on the future avenues. So basically, I'm going to talk about the future avenues of the thesis, conclude a bit, and then talk about open a bit on the rest, on what I've been doing and where it's at right now. So the goal of the thesis was to set the foundation for extending ambient assisted living from smart homes to smart cities. So exploring different prototypes, exploring different algorithms, seeing what we could do. And I just realized that just one experiment led to many more questions and many more areas to explore. So first of all is the data set. We need a larger data set. So we're going to need much more images. We need to collect images at different locations. And we also need to get images at night because we're using thermal images, and that's one of the upside of using thermal images. To explore different algorithms as well. So the one I'm exploring right now is YOLO to perform object recognition in real time. Then there is the embedded implementation part. So improve the hardware. So most likely use something different than a Raspberry Pi. Explore sustainable energy solutions, sorry. So for example, in one of the papers I published, I just ran a few computations based on different research. And I realized that we could power, or at least partially power, the Raspberry Pis using small solar panels. So that could be interesting to move towards sustainable cities. And then there's the entire algorithm optimization on the boards. So if you're going to do something real-time and embedded, you're probably going to optimize it at some point. Then there's the entire smart city aspect. So we're doing profile recognition, but what are the other use of this approach? And I'm going to extend on this later. And then the entire communication aspect. So how do the nodes communicate with the city server? How do they communicate with each other if they need to? What type of protocols do we need to use? So that's just main description of the areas to explore. And once again, that's the summary of the thesis. And the fourth column that I'm going to be talking about just after this conclusion. So to answer the main question of the thesis, so is it possible to recognize people's profiles using thermal images in the city and using deep learning? Yes, it seems to be possible because we're getting around 78 to 80% accuracy for gender and age recognition. We're getting near 99% accuracy for mobility recognition. It seems that using a sequence of images leads to better results than using a single image, but there's no guarantee that this is the best approach. It seems that the Raspberry Pi is not powerful enough for real-time classification. So new solutions will need to be explored. Based on the results on the Raspberry Pi, I don't know if you saw on the other side, in the base case, we had 130 milliseconds for classification, and we're using a camera that's running at 9 frames per second. So even on the Raspberry Pi, we're close to real-time classification, even though the results are not that good. But that could show that on actual deep learning board, we could probably get towards real-time profile recognition. The system could be extended to many more applications, which I'm going to talk about. And at this point, I'm realizing that it's a thermal vision challenge I have to solve before solving the rest. And that's what I'm going to move on to. Well, first of all, a quick summary of the publication. I put them at the bottom of the slides during the presentation, but the publications associated with the thesis. And what I've been working on is basically my idea is to perform a two-stage recognition. So first, you just solve a general thermal vision problem. So you first recognize broad categories of objects, so person, car, or whatever it may be, truck, wheelchair. This runs. I don't know if this is going to run, yeah. So that, well, I'm not used to being full screen. Sorry about this. Okay. I leave this. Okay, it's not really working. Not responding. Okay, maybe I'm going to show this on here. So I've reconstructed a video using thermal images, putting them at around 10 FPS. Actually, it was 9 or 10 FPS. And it's really not going to work. So apparently, using Chrome to play 120 by 160 pixel video is too much work. Wow. Is this the, is it the, I think it's a recording of the session, maybe. Well, can do anything. Working now. Can just leave this. Yeah, okay, it's working. Well, it's going to be quite small. Hope you can see. Because it's just like the actual resolution of the video. But basically, these are the prediction that YOLO is performing on the images. It's actually taking 10 milliseconds to infer, to recognize these classes per image. So that means that's on a computer. So that means that on a computer it could run in real time, but you need to test that on an actual embedded board. And what I've been doing actually on Monday, I've used the same model to extract the silhouettes here. So my idea is to first recognize the objects, extract the silhouettes, and then use a CNN or a vision algorithm on these extracted silhouettes to perform profile recognition, which is the more logical way to go about it. Then we're seeing more and more, because I've been looking to buy another thermal camera because the first one was broken. But I'm seeing more and more approaches using thermal images in the automotive industry. So that could be also interesting to explore these applications in the city. So you could have more data and train more thermal vision algorithms, and maybe data from the cars being used to enrich the data from the city and vice versa. And I realized also that the gate-based approach, which is what I've been saying earlier, was too limited, and that really is a vision problem that you have to solve in the city before being able to bring ambient-assisted living. This is an example of a city dashboard. So when I'm talking about smart cities and a city dashboard, basically, if you imagine that you have a few dozen or 100 nodes in the city that collects data in real time and that performs real-time classification and profile recognition, you could basically gather all of the data in the city and have sort of smart tools, interactive maps, where the city could have a better idea of how the city is functioning, basically. And a quick anecdote, when I was a student in engineering school, I was part of a student club, and we used to organize a festival on campus, so like bring artists and have big concerts and everything. And we need to finance the festival. So what we used to do was we had an agreement with the town hall, the city, where we just stand at an intersection and basically count the number of bikes that were passing by at the intersection, and then give this data to the city, and they'd use it to modernize their architecture. And so I know that some cities are actually interested in this type of data. So that could be really useful if you could generalize to more classes and you could have a wide range of applications. First of all is real-time mobility recognition. So you could see, are there no people with reduced mobility in this area in the city? What does that mean? Does that mean that this area is less accessible than another area? Does it mean that we need to do work at this place? And then recognize, is this public park attractive to elder people or to children or to different populations? So you could change more of the city so that it's more attractive to the people you want to attract, basically, and understand more about the overall city. And that's final snapshot of the thesis. So basically, what I'm doing right now is real-time object and silhouette detection. Actually, I've done this already, even though it could be improved. Then the next step is real-time soft biometrics recognition. So that would be recognizing the actual profile of people. Then real-time event detection. If you're putting back the temporal aspect, if you can use different images and use a sequence of silhouettes and images, you could recognize events. So that's when you could have applications such as fall detection, which could be useful in ambient-assisted living, or some people have already done work on recognizing dangerous or suspicious behavior, or traffic accident detection. So tons of applications on this. And then the most important point is that if you have this sort of system that's deployed in the city, assuming that it has a good level of privacy because you're using thermal images, your cities basically become a test bed where you're collecting data all the time with thermal images. And these thermal images can be used to solve vision challenges. You could also solve very interesting real-time artificial intelligence challenges. So for example, concept drift. If your model works well during the day, how does it work during the night? And how do you retrain a model to deal with the evolving population as well in the city? Maybe there's no children in the city, in a part of the city, suddenly a school opens and you have children. How do you see emerging classes appear in the data? And yeah, so that would be basically lots of thermal data could be used for many different applications. Thank you for your time.
Thank you, Rani. So now we will start with the period of questions, and Sylvia, you can start with some comments about your work and some questions also.
Okay, perfect. First of all, I would like to thank you so much for inviting me for acting as external reviewer, and I would like to thank Rani for the very good job that he has done with such a work, such a PhD thesis, because it is very, very interesting and useful. Actually, the first question was why the gender? Why the need of identify the gender? But you have answered with this slide that you are showing us. In particular, I guess for the safety application, I'm thinking about nighttime isolated places. Exactly. And so on. That is very interesting. And what about the gender identification? It is something related to the way the people walk, or maybe it is something that could be referred to the silhouette, maybe, I'm guessing, wearing some specific clothes or bringing a bag, just like a woman used to do.
Yeah, that's what I was thinking, actually. I think, well, again, it's not responding. Okay, that doesn't matter.
That is a Murphy's law.
Okay, so basically, I thought my hypothesis is that maybe gender recognition was more visual, and that age recognition was more in the gait, in the way the person walks. Mm-hmm. So when they get older, and that's actually like referenced a lot in the literature, when they get older, their gait starts to deteriorate. Sorry, it's a hard word for me to say. And that means that maybe using temporal aspect allows to recognize age more based on gait, but the visual aspect is quite important. In the literature as well, they realize that. I think men have more upper body sway when they move, but there could also be the simple size of the silhouette, because women tend to be a bit thinner or a bit smaller than men on an average. In an average, and a bit smaller as well. So that could be that the visual aspect is more important than the actual locomotion aspect to recognize gender. But I'm not sure about this. It should be tested more, but I think the visual aspect impacts more. But then again, on the thermal image, you have different challenges, and clothing may be less apparent than using RGB images. So that could be slightly different as well still.
Yeah, also maybe the thermal effect could be affected by some gender issue. That is very interesting. And actually, I've got a curiosity. You mentioned that the Raspberry Pi 3 is not powerful enough. And did you get the chance to try Raspberry Pi 4, for instance, or is it something that you do not have the chance?
No, I don't think we have any in the lab. No, we didn't have any in the lab. We had a Raspberry Pi 3, so it was quite handy to just use what was there.
I was curious because we have plenty of them in our lab, and I was wondering.
They're much more powerful, Raspberry Pi 4?
Yeah, they are more powerful, but I guess that maybe there could be some trouble. I am curious about reading something about what could be the difference in this sense. And what about in the even in the video that you show us, there were some vehicles in the background. So there were a person and a car. What about the, how can I say, the intersection and the interferences when we have got some more, maybe more people, more person walking and some vehicles and some other element in the background that could somehow affect the recognition, the identification of the gate activity?
I think there's just one answer. It's more data, because basically, as you can see, the model is not perfect here, because at the beginning of the video, you can actually see a false positive. So at some point, it's predicting a person that's not there, and it's missing someone in the background as well. But that's trained on, basically, I'm using 5,600 images at this point, which is really not that much for 6 classes. But it seems to be able to, even if a car is behind the silhouette, it seems to be able to recognize both. But sometimes it has false positives or it misses some. But I think that could be solved with more data. And what's important as well is that this is just one angle, one camera here. So that's kind of working with the same setup. But it would be interesting to try this at many different angles at different locations in the city to have the system be much more robust. But for an order of idea, I think it's more in the range of millions of images we need to use to have something robust rather than just a few thousand.
Okay, that's interesting, very interesting. A last question, that maybe it is more philosophical and general one. If you should summarize your work in a couple of research questions, which have been the research questions that have driven your PhD study, your PhD thesis?
What do you mean, summarize my thesis in just a few
summarize. Yeah, just identify 1 or 2 research questions that has been answered by the work that you have done.
It's possible to recognize people's profiles while maintaining their privacy in the city by using thermal images. And if you want to bring ambient assistance living, if you want to make smart cities with ambient assisted living, you first most likely need to solve vision in the city. There could be other approaches, so using environmental sensors, but I don't think using tons of contact sensors, motion sensors, the way we do in smart homes, I don't think that would be the right approach in the city because of the ambient pollution and everything that's moving around all the time. So I think that vision is really the way to go towards smarter cities. So yeah, so that would be solving vision, basically.
Yeah, maybe even because other kind of sensor could be more effective in an indoor environment. Since here we are talking about mobility, even in an outdoor environment, we cannot take into account other kind of sensor that could be maybe effective in a different kind of smart environment, indoor environment. Okay, thank you, I'm fine.
Thank you.
Okay, Mickey, it's your turn.
Yeah, sure. Well, I already have a lot of questions, but I'll try to ask a couple the first round, and maybe if we have time, I will ask more in the second round. So where to start? First, thanks for having me here, and thanks for this great presentation.
It was a continuation of your work, so I was just.
Yeah. I really like this, and I like the presentation and the storytelling presentation, the lesson learned part. So that's great. So let me start first with interpretability. One of the main problems of black boxes, as you know, is how to interpret the results. From what I've seen here, there's no way to guarantee that your model is looking at a gate.
Mhm.
Can be looking at anything actually, especially
Yeah,
when you have
very
a
true.
small data set. It can be looking at background, it can be looking at temperature, difference in temperatures, stuff like that. So obviously we're not the first to do something similar to this. There are methods that try to interpret black box models. So have you thought about adding some kind of interpretability work, trying to understand what your CNN is doing?
Yeah. Actually, that was, is that
Yeah,
is that it?
that's that.
Okay.
Yeah, that's the first question. Yeah.
Yeah, I was actually interested in this, but you could ask Kevin, but every time we want to publish a paper, I'm like, I want to do this, and then this, and then this, and then this. And he has to tell me, okay, stop. You need to just stop here and do this, and then you'll do the rest. And basically, I was really interested in this. And I had to, that's what I want to do in the future, actually, with the extracted silhouettes and doing this properly, because I've seen actually just go back to literature review, if this is not going to crash. In the papers I've mentioned, which are the main, the most relevant to the thesis, where people do gender recognition using both RGB images and thermal images, they actually have these, they sort of open the CNN, open the black box, look at the last layers, and really look at what features are being recognized here. And they realized that fusing both modalities was useful because you're getting the visual appearance from the RGB data, and you're getting more of the face appearance from the RGB data, and you're getting more of the silhouette data from the infrared images. And I was interested in this, and that's what I want to do in the future as well. Because if I'm misclassifying someone as being an adult when they're an elder, or a male when they're female, I want to understand why. Why am I misclassifying here? So that I can understand what I need to fix in the model, or how I could train it differently, or how I can make it more generalizable, or how to understand my classes better and understand what really makes the difference. What are the salient features that make the difference between two different classes? So yeah, so in the thesis, I have not had time to do this actually, but it's something that I'm planning to do in the future to improve the model.
Fair enough. By the way, so I'm looking at, so I have two screens, one on the right, on the left, big screen.
Mhm.
So like it's not, I'm like not looking at you, I'm looking at you when I'm
Okay,
looking
yeah,
at the right screen.
I
Yeah,
know which
so
camera to get.
yeah, just remove that confusion. So that's great. So the second question is, so let's put it this way. If I were you, I would, if I were you at your place, the first thing that I would look at is pose estimation. Like, yeah, so this problem of recognizing age, mobility, and gender has been widely explored using RGB cameras.
Yeah.
And so my first intuition is to try to leverage that knowledge, those models that have been built on billions of images.
Mm-hmm.
So there are all the models that do that using RGB images. And so this has two components, two questions. Like the first one is, why not trying to transfer some of that knowledge to thermal images using some kind of transfer learning approaches? And the second one would be about the pose estimation, and I'll give you more details about that. But let's start with the first one. Have you thought about doing any kind of transfer knowledge or transfer learning from RGB models?
Yes. But the main difference, actually, I wanted to do this, but the main thing is, when I said I made a conscious choice of not pre-processing the image, that's where the issue comes, because all of these RGB models usually just work with the silhouette. They do not work with an entire image with a background and just an 80% of noise. And because of the initial choice I made of using the entire image, I could not directly use these models that were trained on silhouette specifically. But for YOLO right now and doing object recognition, I'm actually using a model that's pre-trained on, I think it's Coco, on the Coco data set. and the COCO classes on the image data set. And I'm using this right now, and I'm just fine tuning it on my images. So it's already pre-trained to recognize some of the images. So I'm doing this right now, but back then I did not do it because I just used the unprocessed images, and it seemed like, at least from what I saw in the literature, that a lot of these models doing really gate approaches, they're using gate energy image, and they're using extracted features from the actual silhouette and sequences of silhouette, and not an entire image in an urban environment. So I could have done what you're saying, but it would have required extracting the silhouettes beforehand, and I hadn't taken the decision at this point to not do this. But I think that would be the way to go, because there's no point in starting from scratch if something has been done before. Or it's just
this is what I mean. I mean, was that decision driven by something?
Yeah.
That. Yeah. I mean, why did you make that decision? This is what I mean.
As I said, I made that decision because at the time I thought that if I had a method to extract the silhouettes on my images in the lab, I would.
Okay, so what I mean, if you can go back in time, would you do that differently?
Yeah. With the knowledge I have now, I would just start with vision.
Okay, sounds good.
Yeah.
So this is also related to the second part of that question. So the pose estimation, 3D pose estimation, is widely established in computer vision. There are a lot of open source models that you can use to extract very precise pose data from RGB images. So what I mean is, have you thought about when you collect data, you collect RGB in addition to IR images, and you use pose estimation from RGB images, and you simply apply the joint, the detected joints to your IR images and retrain them so that your model is really looking at gate. So if you do that, something like that, you are sure that your model, your CNN, is, since it's going to be using the joint data, you're sure that all the features will be about joint and about gait and about how they walk and stuff like that.
Yeah. Okay. So what do you say? So
well, do you think this is a viable option?
Yeah, but there's one main issue, is that the experiments we're doing, we're allowed to do them because we're not using RGB images. So basically, if we were to use both RGB and infrared images, we'd need to have authorization. At this point, it would not be sort of anonymous anymore. We would need to, we would actually be able to identify the people with the data. So then we could still see if it's possible, but we need to ask the proper authorizations. But one good point about this is it would make labeling much easier as well, because having a visual reference on the RGB image makes it easier. And we've also thought about extracting the skeleton. That's something we've considered, extracting the skeleton and the joints from the infrared image, but we've decided to go with other parts. And that's the thing, is that you have to understand, I came from the very smart home mindset and activity recognition, then gait recognition, then computer vision. And I think on this, we're at the intersection of sort of computer vision and gait recognition. So there could be very interesting avenues in combining both. So first doing vision to recognize macro sort of categories of objects. And then when you're working with the person, apply gait recognition. I think that would actually be the best approach. Fusion of
Sounds
both.
good. Sounds good. So I'll ask the last question in this round, and then I have maybe a couple more if we have more time. So could you? And again, this is me very interested in this project. So this is great work.
I'm interested in talking about it. I have no one to talk to.
Yeah, I was just like putting myself in your position and trying to understand and think differently. But this is great. So could you go to page number 17, if possible?
17.
Yes. Yeah. So.
Oh yeah.
I think, so I think you mentioned something about the limitation of the 5-fold cross-validation here, and the fact that you had some like the same instances from the same user in both tests and training set. Why didn't you use leave one subject out cross-validation, or leave one sequence out cross-validation. Like each time you, since it's a small data set, so you train your model on all participants and you hold on one, and you keep repeating that in a cross-validation fashion.
I want to say it's small, but it's not so small that this would be. I think it could be a good approach. First of all, because I'm guaranteed that the person I'm testing this on has not been seen by the model. But we're still talking about 500, 550 instances, I think, at that point, which means I would have had to train to do this loop 540 times.
So instances here, I mean a sequence of,
yeah,
not images, right?
But at this point, I'm going to be honest with you, I just lacked experience a lot in deep learning. So basically, the way I handled my data was not the best way. So that was the very first approach. But yeah, I think leaving one out,
or at least you can do the cross validation on the subject level.
Yeah,
on the.
What do you mean on subject level?
So what I mean is when you have you have one sequence, like a multiple images belonging to the same subject.
Yeah.
So that will be one sequence. And when you do your cross validation, you do it on sequence level. So you hold a particular number of sequences for training and the rest for validation, so that you are sure that the same subject will not have the same images in both training and testing.
Yeah, that's 100% what I should have done at this point. I just did not sort the data, and I was excited to get results with the CNN. But yeah, that's what I should have done.
Sounds good. I'll stop here, and if I have time, I have a couple more, but thanks.
So, my turn. I have similar question to those from Mehdi.
Okay.
So the first one is I noticed that you tried transfer learning and it did not go well. But the struggle in your project is the quantity of data to perform well, to generalize the proposed approach. So did you think to other solutions to overcome these limitations?
At the time, no, actually, the only real solution I've used to deal with little data was not transfer learning, as I said, because of the fact that I was working with unprocessed images, but it was simply image augmentation, actually.
Okay.
It was just applying random transfer.
And now, if you can try another solution.
Oh, yeah, I would. I think what I would do is actually the same thing Mehdi said. Well, first I would use YOLO to extract the silhouettes, and then with the silhouettes I would reconstruct silhouette sequences, and then probably work. I would try to build to use the same features that I use in RGB models currently, but in thermal version, and I would use pre-trained models of RGB data sets and try to use them, fine-tune them on my model, and then
and future learning, it's not an avenue.
We've tried actually one-shot learning, was it Simon's networks? Because we wanted actually to see that, because there's also interesting avenues that we want to see what the model could do in like semi-supervised learning or unsupervised learning. And the good thing with Simon's networks is that not only is it one-shot learning, so it works well with very small data set, is that since it's based off similarity measures, we could also try and see if we could see emerging classes, sort of, because we're working on similarities and direct classification. But yeah, that would be an interesting avenue, I think.
Also, another question, it's do you know that the recent trends in machine learning is robustness, explainability, and responsibility? So what will you do to tackle these trends?
Well, you said
your project.
You said robustness, interpretability,
explainability, and responsibility.
Well, robustness. Well, I guess the only answer I could find is more data. For robustness, more data, but like actually smart, like collected in a smart way, so different angles, and try and cover most of the scenarios we'd see in the city and a realistic application. In terms of interpretability, as I said, I really would like to like open the black box, open the CNN. I don't know enough at this point right now to do this, but I want to learn how to do this and to be able to explain the models. And responsibility, would it have to do with ethics or sort of privacy? Well, first of all, that's the main choice of why I'm working with thermal data. But I also thought about the fact that you would not necessarily need to sort of store the images that you've captured of people. Obviously, you want to store the image because more data is usually just more useful in deep learning and in vision. But you could also think about applications where images could just be classified, basically, and the results of the classification could be sent to the city server, but the image deleted. So then you've got much more privacy. And so, well, you could, even if the system gets hacked, for example, there's no images to find. So that could be maybe a more responsible approach.
And the last question for now, can you explain with more detail how will you handle the concept of drift, the concept drift in your project?
First, I need data that drifts. So I need to collect data at night, for example. So that's what I was thinking. Collecting data set at night, collecting data set different time of the year. So maybe in the winter, and get like your cold fingers pressing the tablet. So I have to find a solution for this. But basically doing this and first training a model on one of the data sets and seeing how it performs on the other data set, then doing it the other way around, and then use interpretability to see, well, why does it recognize that a person male or female are the way they are in the summer and why they're the way they are in the winter, and then possibly realize they have something to do, I don't know, with clothing or whatever it may be, or differences in the heat. And then I don't know enough yet in the future, but then try and understand what are the very underlying variables that sort of lead to the model to make the decisions it makes, and try to see how it could affect them.
Yeah, but there is another drift between the prototype and when you will push the model in production.
In
MLOps. So there is a drift about the performance, but how do you monitor the performance, and how do you detect that drift?
That's super interesting, because that's something I thought about at the very beginning of the thesis, because how do you recognize the performance of a model without ground truth? Because we're using the nodes in real time in the city, and people are passing by. The node is sort of outputting classifications, but since the images, you cannot necessarily recognize yourself if the person is a male or female. It would be hard, but that's why I thought that distributed application could be useful, because if you can guarantee that someone is passing by in front of a node and then another node, and then compare the classification of each node, or have at least 3 nodes, you could sort of build a distributed system where that's the hard part, if you can guarantee that it's the same person that's passing by in front of every node, you could basically go with the majority decision, and you could see when one node would start drifting away from the classification of the other nodes. So if you imagine a distributed system, maybe it could be self-sustaining by comparing its result to the other people. But then again, you need to identify the person. That's the hard part. And other than that, because you need some type of, or you need periodic times where you can actually collect ground truth. So sort of have, I don't know, every month or whatever it may be, to do an experiment and to really see if the model is still performing well. That would be time consuming.
Thank you. By the way, your presentation was excellent, and your thesis is one of is the best that I read since I'm
really?
Professor. Yeah.
Thank you.
So, ciao. It's your turn.
Thank you very much. Do you hear me well? It's okay?
Yeah.
So I thank you, Rani, for your presentations. I don't have really specific questions because I had like 3 years plus to ask them. To begin with, I just want to say that it was really a pleasure to co-advisor you during that adventure. You are really a person that is working hard, really methodical. We saw that you were working, creating a journal, some Excel sheets to track all the try and models that you built. And you really worked to optimize the results that you could have with the available data that you had in hand. So you work really hard on that.
Thank you.
So I have maybe specific questions that you didn't cover that much in the presentations. In your thesis, you made the optimizations of the hyperparameters in your different models by doing it in a custom way. Would that be possible to use some hyperparameter optimizer tools like the ones that are proposed in Keras and so on? So
yeah, such as TensorBoard or things like that. And I think it would have been. I think I tried to install TensorBoard, but I was already halfway through my spreadsheet approach. So then I didn't end up using it. But I think if I'm doing this, and I'm actually going to do this soon again in the future, I'll do this more professionally and methodically using tools that are meant for this. But yeah, because that was really quite an intuitive approach. But I realized it could be optimized with the right tools. So yeah, that would be what I would do now.
Okay, so a lesson learned, if you want.
Lesson learned, yeah.
I mean, the way that you work, that was what was interesting. That it was a way to learn from you. That okay, I'm like tweaking that parameter, and that's the results. When you're using a optimizer like that, is doing the job for you. So at some point you get like the optimal setups, and you don't learn that much using those kind of tools. You can track you have the different parameters, and you can track the optimizations, but in some way, usually you don't look at the different try and the logs. You just use the last results and you work with that. But yeah. Another question is about you talk a little bit in the last question that you received, but it's like more an open questions. But what would be the challenge of using different camera angles, and maybe also different, if you're using an hybrid inputs, like using RGB camera, RGBD camera, thermal camera, the same on the same scene with different angles. What would be the challenge to like integrate all those inputs in a deep learning approach?
First of all, first of all, it could be a resolution difference. Well, that's the first thing I'm seeing. But there could also be like something to do with illumination, and depending on the scene, RGB data at a certain time of the day or in certain position, the RGB data could maybe not capture such a clear picture of the scene compared to the thermal data. And it could be the opposite as well. If there's a lot of light and a lot of heat, maybe you've seen some of the images. You could have things or people that just look like ghosts, and could maybe be hard at some points to even use both images because they would capture the same scene but in such a different way. And then there would be the real-time aspect. So basically trying to fuse data from two modalities in real time and then perform classification would be quite costly. That's one of the first things I'm seeing. And yeah, not sure I'm seeing more. I need more experience. Well, I'm going to have time to get more experience with Fusion. But yeah, I need more experience in Fusion, but that's what I'm seeing. Resolution difference, like environmental differences as well, and to fuse the data right.
Okay. Another open question is that in the recent years, let's say like the last 2 years, there's a big trend around the vision transformers. And in your thesis, we used the RNN GRU approach, but we discussed at some point of using like attentions models and so on, but we decided to focus on different aspects. But with the data we have, and let's say that we have the hardware to use to create some vision transformer models, would it be possible to replace the RNN GRU approach with the vision transformer with the data we have at the moment?
I don't know if that's enough data actually, but if there are some vision transformers that are pre-trained on some similar data, I guess we could try, but as you said, we need the hardware first. And yeah, I need more experience with transformers, but I think could be a good approach. But at the same time, do vision transformers, they're just a vision model, so they don't necessarily take into account the temporal aspect of things. But maybe they could replace the CNN and then use the temporal aspect of things as well. But that could be a right approach, but I just don't know if we have enough data. Probably need pre-train the models.
Okay. And last questions, and it's open questions too. So for collecting the data, we deployed the camera in a city setup. So the models learns about in some way the context of the surrounding the user. So there was the background, and in your models the background is integrated in the models that you build in some way. So it would be difficult to transfer, for instance, your model to another setups, like let's say inside a malls or in an hospital or a big public space, but inside a building. Would it be really difficult to just like take your thesis output and try it in a different environments with the same hardware, same cameras, and so on?
Yeah, that comes back to what Mehdi said, is that I don't really have a guarantee that it's really looking at people and at gates. Well, because of the trend and the improvement of the trend, we can sort of say that it's not just classifying the background. But I think we would need to have, just draw a curve, but I think we need to collect data from sort of 10 viewpoints and maybe 20 different viewpoints, 30 different viewpoints, and have a model trained on all of these different sort of angles and different places, to then try and converge towards understanding what really constitutes a silhouette. And then at this point, when the model would be general enough, maybe it could be used in a different setting, or simply collecting data indoors in similar environment and have an indoor model, outdoor model. But then again, it's better to have just one general model that does things better. But yeah, I think with this current viewpoint and experiment, I think if I were to put this indoors, it would not perform as well. Really would not perform as well, because the background may have a lot to do with it. And if I'm slightly tilting the camera and seeing people walking at 45-degree angle, I think I will have quite a big drop in performance as well. So I would most likely need a lot of different viewpoints to have better generalization.
Okay, great. I think that's it. So again, congratulations for your hard work for the thesis, and it was really a pleasure to work with you, and we will continue to work also together. So
yeah,
that would be a really fun and interesting.
Thank you.
Thank you.
Go if you're down, maybe.
Okay, I will join my colleague to congratulate you. I think you did a good presentation, and if all the students were as autonomous as you were, I think our job would be very easy.
Thank you.
So I think it was a pleasure for both me, Charles, and also the whole is there today. I have also to state that we were very limited in the lab from artwork perspective.
Yeah.
So everything we did was from conventional computer with a
So,
good GPU, but not an outstanding GPU, just an average GPU. So this limited a little bit our experiment. I won't ask many questions, but one thing that we haven't discussed much is the labeling in the ground truth. This is some recurrent problem that we face in pretty much all field of ambient intelligence. It is difficult to obtain ground truth, and then we try to evaluate the model that we developed, but we based our evaluation on some estimation of what is ground truth. And I think in your case, I would have liked it if you could discuss a little bit about the subjectivity of the labeling and what are the good things about it and what are the limitations of it.
Well, as I said first, there's some kind of fuzziness in it because, for example, as I said, the difference between what constitutes an elder and an adult and an elder is based on an arbitrary, a convention that's used in the literature and on my subjective appreciation of the scene. And same goes for gender as well, because I'm looking at observed gender. So I'm not going to people and asking them what really is their gender. So the ground truth is only as accurate as the observer is. And there's also we talk about it a bit, adult and child as well. So there are some children that are in high school that are as tall as adults, but I can tell that they're children, but like in the data set, classifying them as children might lead to lowering the imprecision. And there's also sort of a bias as well, because it's like, am I collecting data to get the best possible results, or am I collecting data to be the most realistic with what's happening in the street? So there's a big bias from the observer as well. And yeah, I think that's a big challenge. And also there's the hard part of like interference, like I said, so to collect the ground truth of different people, but that's very specific to this problem, very specific to the experimental setup of not having a proper solution with that current approach to be able to label several people walking by the system at the same time. So we need much more advanced approaches with some type of real-time communication between the tablet and the Android and have some real-time feedback. Or I'm thinking as well, maybe there could be a way, because ground truth is such an issue here, to have agreement with the city, because there's basically CCTV cameras in a lot of cities. I don't know how many there are in Saguenay, but to have some sort of agreement to be able to have an experiment in a place where we know there are CCTV cameras, and to be able to like privately use this as ground truth, so that we could label much more data much easier. We just need to basically run the thermal nodes and then compare the actual ground truth, assuming the cameras are high enough resolution so we can tell someone's gender and age. And once again, it's observer biased. But yeah, that could be useful to have a RGB ground truth to compare it.
I guess one point also that I wanted to discuss is that in a way we decided that we fix the boundary of each of those classes. Like we say someone is going to be classified as an elder when they look over 65. But perhaps in some way, the model actually learned what it is to really be an age person.
Yeah, so going the other way.
We are the one who are wrong. Because, for instance, we can see some people at 65 that can walk very fast. Some of them actually run marathons.
Yeah.
So are they really age people? I'm not sure. And in a way, I wanted to see if you could do you have an idea that maybe in some way you were the one making mistake, or is it not possible to do this kind of analysis?
I think I was making a mistake, but well, I'm just going to say, I think we'd need lots of data to discover one thing that would be emerging classes and like I would like to have so much data that I could allow the model to discover the boundary between classes by itself, and to have the model actually tell us what classes are. So basically, I'm thinking we want to do ambient assisted living, and I decided arbitrarily that elders may need more ambient assisted living, which is based on what's happening in the literature as well. But maybe people who have sort of limping problems could have also mobility issues. And I'm not necessarily classifying them as elders. So maybe the model could actually learn what mobility issue looks like, and then tell me that this person who is an adult, who I would have labeled as an adult, actually fits into the category of people that might need ambient assisted ambient assistance, live assistance. So actually, I think there would be an input from us, but if we have enough data, we could have that's why I'm interested in the unsupervised approaches as well. So to let the model discover and teach us about the population as well. And that also comes from the complexity of what is a profile. So I'm using the term profile, but there's so many different aspects to someone's profile, just like personality, identity, or whatever it may be, that I'm just looking at one aspect because at some point I have to make a binary decision, but there could be more fluid, and there could be more different aspects of people, and someone could belong to several classes that all have a different use in the city for this system. But yeah, I think having a model and data-centric perspective could be more useful than having my biased perspective as an observer.
Okay. And considering obviously are those boundaries, for me, the results are in a way good enough for the categories, because I do not expect that just from thermal imaging, when I observe the image, I do not expect that we could reach a point where we know 99% of the time if it's a man or a woman, considering what they can observe. So for me, the results are good, but one question that we did not discuss is how the error are distributed among the class.
Oh yeah.
Because it's more important to me that they are evenly distributed than the fact that we cannot reach 90% at least. Because if we know that, let's say 80% of the time we can guess if it's a woman or if it's a man, but we know that the error is evenly distributed among those two classes, then our results are statistically interesting, because we can start having, information about distribution in the city. So did you check a little bit how your error is distributed?
Not really, because I've used basically precision, recall, and F measure, but I did not really dive into really like which one, like in what sense the misclassifications happened. And that's something I should have done, and I should do in the future as well, I think. Because as you said, like if we realize that our model is heavily biased towards having false positive, but only in one direction, that could maybe allow us to tweak it better to make it more balanced. Because as you said, because of the way we collect, because of the fuzzy interclass boundaries and the way we collect data, we're already capped maybe at 95%. I don't know, we could not reach this, but at least it should be balanced.
And it also goes in the sense of the comment of Julien that we are starting to talk about making the AI more responsible, because this is part of this team where we try to ensure that AI will not promote bias that we have in our society. So I think that in the future, this is something that we need to analyze more, the type of bias that could be hidden in the model, and hopefully it's not biased, but we'll see, I guess.
True.
I would have other questions, but I prefer, I think, letting the other people ask more.
So we are starting the second round of questions, and Sylvia, you can go first if you have some other questions.
Actually, I have no other question, because we have widely discussed. I'm happy with the discussion and all the details provided.
Okay, thank you very much. Eddie?
Yeah, I can go next. So let's imagine you deploy this in a real environment. Are there any environmental factors that you need to account for?
Yes.
Things related to like well, external temperature, humidity, fog, rain, seasonality. And so how do you account for those factors?
Well, that's the thing, because the project spans over like big area, and there's the very engineering side of it, of where we put the nodes. Because, well, first of all, as I said, the nodes should be invisible to the user, but at the same time, they should be positioned so they capture a lot of the silhouette. And as you said, if we're putting them in a challenging environment, I need to actually try it and see how it works. So, like, for example, if I'm putting it in a hallway where there's a door that opens and closes, like in a building, wherever it may be, changes in temperature may bring fog, as you said, on the lens of the camera. But that's something I could only discover by doing more experiments, which is something I'm going to work on. Actually, I started thinking about making the prototype smaller right now, so I could have more options of where to put it. And yeah, so I think I need to try it in the winter. Maybe the battery on the board is going to be drained quicker in the winter as well. So that's something we have to think about. It could overheat in the summer as well. We have to make sure that we're not putting it directly in the heat. The heat of the sun on the prototype could affect the quality of the thermal image as well. And even variations, I've seen variations of temperature throughout the experiment that have changed the color of the silhouette from being more, as you can see, purple to being really yellow and bright. So yeah, so there's definitely, like, the only way I could answer these questions is by doing more experiments in different places. And that's one of the things I'm going to try and do, because I'm going to do my postdoc in Sherbrooke. And I'm going to take the prototypes and see if I can have experiments there. And the idea is to try and collect data in different locations and in different conditions as well. So, yeah.
Yeah, it would be interesting to try to think about how you can standardize your measurements.
Yep.
To account for seasonality.
But that would be a feedback loop, because actually it'd be like collecting data in the winter, collecting in the summer, seeing how it's affected, and then maybe even have a learning algorithm that learns how to adapt to the seasonality. But then you'd have some sort of temperature sensors as well on the prototype. So then you could really embed the prototype in the city and use ambient moisture, ambient temperature for the algorithm, like as an input to an algorithm that would then apply some sort of post-processing filter on the images before being used by the other model, the actual model. That could be useful.
Yeah, we talked about sensor. We talked about sensor. What was the mic used for? The microphone?
For the Raspberry Pi, it was just a standard USB microphone. I don't really know.
No, but what is? I'm sorry. What is it used for?
Oh, nothing.
What was the goal of that? Okay.
The goal was multimodal profile recognition. So basically, I read that paper from Castro in 2016. And what they did was use sound and RGBD data to do gait recognition. And the idea was that I wanted to collect sound and then synchronize each image with the bit of sound it's associated with, and to try and see, or actually the sequence of image. Say someone walks by in front of the camera in 2 seconds. So I'm going to take that sound bite of 2 seconds, and I'll try to do some sort of what was it called, MFCC, or there are some features that could be extracted from sound, or even like a Fourier transform and all of that could be used on sound, and then have one part of classification with the sound and one with the image, and have either early or late fusion, and see if the sound brings us more information. But I didn't do that because first, even just synchronizing the sound would have been a long task, and then processing the sound and making sure we have the right chunk. And then I'm expecting a lot of noise in the city. So I'm expecting that the sound may not lead to really good results, at least outdoors. And there's also the privacy issue. If people are walking by and talking and can hear their conversations, then that could be an issue. So we'd actually need to discard raw sound after extracting the features. But yeah, that was the idea, multimodal recognition.
Yeah, I just wanted to check if you used it for adaptive sensing or something like that to reduce battery consumption, because down the road,
not yet.
I mean, at night, for example, if you want to reduce battery, you might use a microphone to only turn on that sensor when
Oh, yeah,
you
that's
detect something. So, but yeah. So speaking about the device or the hardware, was that a requirement that you want something that operates in real time and with like a low power hungry device, or it's simply that's what you had?
Well, the entire idea of the project was to do this in real time because if we're recognizing profiles of people in this, well, if you want to extend ambient assisted living from smart homes to smart cities, there is no reason to do this if we cannot guarantee that we have at least some near real-time results. Because if I want to recognize an elder falling on the ground to know if I need to send an alert to, I don't know, like a hospital or anywhere so they can bring an ambulance, I need to have some type of real time. So that was one of the constraints of the project. But once again, we're limited with by the hardware that we had. So I used the best board I had, but it's most likely still not powerful enough. But I think the real time component is crucial in this project, even if we don't get to there right now or in a few months. But
okay,
it's really
so in the future, if you'll be working on something similar to this as a continuation in your postdoc, I invite you to look at GPU powered or equipped device, look at Xavier, Jetson Xavier or Nano, and the NVIDIA has a lot of frameworks for real-time processing of images. They have something called DeepStream it's a library built in C, and it's super speedy, and so it's very powerful. So you can easily build what you want with a high resolution actually in real time. Yeah, I think that was it. Those are all my questions.
Okay, thank you.
Thank you.
Okay, so I have maybe one or two other questions. The first one is for the deep learning architecture optimization. Do you thought to use, for example, Bayesian optimization, and if yes or not, why?
No, because I didn't know about it. To be really honest, so I just basically I went I went with it with a very intuitive approach at first, and then I saw in the literature that grid search and random expression were some of the things used, but I've not.
And what is the size of the solution space in number of solutions?
Number of solutions, what do you mean?
It's like number of combination set of architecture or.
I need to look at it, but would be something between 200 and 300 different models.
Okay.
So, basically it was adding layers and then changing parameters, maybe even more. Yeah, I left the computer running for 3 months, basically.
3 months.
Yeah, that was about the optimization time on this hand.
I think it was my last question. So, maybe Charles,
Thank you.
Do you have some other question?
No, I'm fine.
Okay.
I don't have other questions.
I'm fine too. Just a quick comment to also answer Betty. It's also a question of trade-off between cost and power. You haven't mentioned the cost, but we are trying to keep the not. Because the target was not big cities, but smaller towns.
Yes.
So this is important. This is an important aspect. But other than that, no more question from my part.
Okay. So the question period is over, and the jury will retire the lecture rate, and the candidate is available to respond to questions from people in the room.
Yeah.
So
just a second. Luc, can you
Est-ce que tu es là, Luc?
Non? OK, je vais les transférer moi-même.
Oui.
Ah, tu es là. Peux-tu transférer Sylvia, Mehdi et Charles dans la salle jury?
Oui.
Et puis, il ne faudrait pas que les gens voient la salle jury non plus. Ça serait quand même bien. Merci.
Thanks for the presentation. Thank you. I have a question. How did you deal with uncertainties in your database? Because, like you said, you was like some positions, and it was limited to 100 hertz, and like for long, for like compensation for the human, it's like they from 80 to 250 or 260 hertz. So there was like uncertainties. In addition, for the thermal cameras. As you said, like for like it depends on the season. What season there's like data was limited. And like sometimes in winter it was for somebody where like changing this. I mean, like I guess should be a big accuracy as well. So all of these like counted as uncertainties, and AI like models don't deal with uncertainties.
Well, first for the microphone, the 100 hertz microphone was only on the first prototype. So actually on the second and on the first prototype, basically what I did is while it was sampling amplitude at a frequency of 100 hertz. So as you said, it's not even real sound at this point, it's just more amplitude variation. And then I used like averages and lows and highs. But these were the first results. Now for the thermal images, I ran all of the experiments in the beginning of September of 2020. So that was like the end of summer / beginning of fall. In terms of uncertainty, I did not do anything manually or pre-process it in any way to deal with the uncertainty, because the idea was that at the end of the day, we want like a model that could work in the city without having to touch it like in any way, shape, or form. So the idea was that we wanted the deep learning to recognize people's profiles despite these uncertainties. But like the only way to deal with this, in my opinion, is just more data so you can generalize better. You can see an adult wearing a big coat, wearing a small coat. But as you said, like depending on the season, that things that would change.
And also, like I would just like to highlight maybe like those uncertainties, like they can like pick those and they don't need like to develop more the model. I mean, like because like even you have like more data and you have like implementing like optimizations, those uncertainties, but they cannot like go over it. Like you need like to have like some like better solutions or like some solution, just like to go the rather than the data. That's what like I want to say.
Oh, you mean like, would it be better to use like higher resolution?
I mean, like this should be like idea, just like to highlight.
Oh yeah.
In general, I mean.
Yeah.
Because like I
oh yeah, I see what you mean.
Yeah, I was like working for the ANN.
Yeah.
By just like the applications and hostings. But we had like there was like good results, but at the moment there was like some deviations in the results, and it was like we don't have like too many variables so like to highlight everything like what's going on. So we have like some uncertainties, so the model cannot deal with these uncertainties. Okay, so that's like I pick the results without like rather than like focusing on developing the model or like having more data. That's what that was.
Okay. Yeah. Okay. Well, I could use higher resolution, but
maybe like I mean, maybe that's like have like better results rather than just like spending.
Yeah. True. Yeah. Because if I don't fix the problem at the source,
exactly.
There's no.
Because like when you have like higher data, new sensitivities will increase. That will affect the results.
But the thing is that, well, I'm using thermal images like for privacy reasons, and I'm kind of afraid that if I use too high resolution, well, first of all, it's quite expensive, but also like you could maybe recognize more about people, and then you'd fall like between the tipping point where it's not anonymous anymore.
Yes.
So yeah, but yeah, for sure, like we've gone from 8x8 when we realize it's just not enough. Like there's more noise than information. So then 160 by 120 seems to be like starts to be workable. You can work with it, but yeah, probably need like higher resolution. But then again, it's a cost
balancing, because like the higher resolution, like the more processing power you need to actually process the image in real time. So yeah, it's just a balance.
Oh, that's interesting.
Thank you.
Luc,
Luc
a commencé à ramener les gens.
Sinon, je vais le faire. Ah. Placer vers. OK, c'est bon. Et tout le monde est là. C'est bon. Tout le monde est là.
Okay. Donc, Rani, Monsieur Rani Bagheza,
C'est ça.
donc les membres du jury ont délibéré. Il y a quelques commentaires, c'est genre des coquilles, rien de grave là. T'en discuteras un peu plus longuement avec Kevin ou avec Charles, mais de manière générale, ton travail est excellent. On a beaucoup apprécié ta présentation, ton document de thèse, ta thèse, et donc on te décerne le grade de docteur, donc de PhD, et avec la mention excellent. Donc félicitations.
Merci. Bravo, c'était une super présentation.
Merci.
Félicitations. Incroyable attitude pour répondre à vos questions. Ça, c'est ce qui m'est un peu passionné. Tu maîtrises cette matière. Fantastique.
Tu peux être fier de toi, Rani. C'était
Ouais.
de l'excellent travail.
Merci.
Excellent.
Félicitations, Rani.
Merci.
Félicitations. Congratulations.
Congratulations.
10h33. Hey, thank you again, everyone. And I wish that I could have a drink with you to celebrate. Sylvia, of course, sometime in the future, I will have a drink with you. And Mehdi, I hope that I will see you again in person sometime
Sure.
soon.
Yeah, me too.
Yes.
All right. Thank you all. Have a good one. Bye.
Bye-bye.
Et Rani, on se reprend pour le pot de
Ouais.
thèse en personne.
Oui, c'est ça. J'ai déjà trouvé un appart sur Sherbrooke.
Cool. Ben, je pense que là, on va te laisser décompresser. Faudrait avec Kevin se préparer une rencontre le début de la semaine prochaine, peut-être, pour juste conclure, faire un wrap-up de la thèse.
Mm-hmm.
Pour les petits commentaires pour le dépôt final. Puis on discutera aussi de la suite à ce moment-là.
OK.
Donc, dès qu'on presse, on est jeudi. Je pense que demain, tu peux te lever tard. Puis,
j'ai bossé sur les index. Merci.
All right. À plus.
À plus.
Bon, regarde, tu as aussi une
Bye.
belle toge.
Ah, merci.
J'aurais pas dû te le dire en fait, parce que c'est dans une boîte.
Ah oui. Je dois le mettre maintenant ou... Non.
As-tu le temps qu'on aille dîner? Je pourrais t'amener dîner après. Ben là, j'ai un peu de travail, là, puis
Ouais,
je vais te chercher à midi, mettons.
OK, ouais.
Ça te va-tu?
Ouais, ça me va.
C'est bon, je te revois à midi.
OK, merci.
Je me dis de faire une qui donne son
Mais le chapeau, il est très non.
Non, on va recommencer ça.
Bye bye, Sylvia.
Ciao, Sylvia.
Ciao, bye
Ci
bye.
vediamo.
Ci vediamo. Bye. Kevin, hope to meet you in person in Lisbon next year.
Yes, hopefully.
I hope.
Bye bye.
Spero. Ciao, ciao.
Bye bye. Ciao.
Thank you.
Thank you. Bye.